Hello everyone, and welcome back to the Kohi Game Engine series. Today we're going to take a look at making some generic render buffers. So we've talked a little bit about Vulkan buffers so far, and Vulkan buffers are responsible for holding data, we know all that. But there's an issue sort of with the way that they're set up so far. So the problem with the Vulkan buffer as it stands is it's Vulkan specific. And the concept of a buffer really is at a higher level than just Vulkan. OpenGL has buffers, DirectX has buffers. And so we really need a more generic way to access buffers from the front end. And we can move some of that logic to the front end and offload some of that logic from the back end. So one of the other things that we need to address as well while we're making all of this generic is we have in the Vulkan buffer all of this free list logic. And really the Vulkan buffer itself shouldn't have to know anything about free lists. It shouldn't be managing that. But because we didn't have sort of a front end buffer or render buffer, that's where we had to put it. And so what we're going to do instead is we are actually going to create a new type called a render buffer. And the render buffer will basically contain the free list, but it'll also contain a sort of a void pointer, which can get cached to the internal buffer type, which in this case will be a Vulkan buffer. So it allows us to have that sort of front-end, back-end separation, but will also allow us to keep the generic bits out of the back end. And this whole thing is actually going to be required for the next feature that we're going to implement, which actually starts in the next video. So we have to actually knock this out now and get it out of the way. So the very first thing I'm actually going to do is we are going to take all of this this Vulkan buffer logic actually out of this separate file and move it into the Vulkan backend. And the reason that we're going to do that is because right now we have to sort of pass this Vulkan context everywhere, and that's kind of annoying. And so we can actually simplify our API a little bit just by moving this stuff to the Vulkan backend, because it already internally has the context object that it will need and can reference that statically. Since there's only going to be one sort of Vulkan instance, or one Vulkan context as it were, that is probably going to be the best way to go. So the first thing I'm going to do is I actually have all of this stuff already moved and converted and separated out. I've gone ahead and done a lot of that work ahead of time, so we're just going to kind of step through it here on video. So I'm going to start this off by removing the Vulkan buffer definitions and declarations here. So the Vulkan buffer C and Vulkan buffer H, I'm going to move those to the trash because we do not need those anymore. And instead, I'm going to go to, first off, renderer types, INL, which actually I'm already in. And I'm going to add a little bit more information here. So one of the things that I'm going to add is an include for free list. And I may see if I can actually figure out a way to do this without having to include free list here, but for now this is just sort of the easiest way to do it, and I'm fine with it. So the first thing that we're going to do is we are going to declare something called a render buffer type. And I'm actually going to put this right after our render path structure, so right here. And this is going to be an enumeration that allows us to declare different types of render buffers that we can have. So the first and default is going to be an unknown type, which has no equivalent in the backend. So if we actually try to create a render buffer of that type, it's going to throw an error, meaning that we need to configure, or at the very least pass through the type of render buffer we want to create, and then the backend should be smart enough to actually go ahead and set that up. But from there, we're going to have a vertex buffer, an index buffer, so all things that we've seen before, uniform buffer, those are things we've seen before. We're also going to have something called a staging buffer, which is used for staging purposes like we've seen before in the Vulkan backend. We are exposing that concept to the front end, but we may or may not actually wind up using it. And then we're also going to have a read buffer, which is basically a buffer purely used for reading purposes. So as I have here, something to copy from device local and then read out of the buffer, but we don't actually need to modify it in any way. So if we've got a block of memory that we just want to read from and we need a buffer to do that, this would be the type that we go ahead and implement there. And then we're also going to have storage buffers in here. Now, we're not going to support all of these right out of the box right away. The main three that I'm concerned with here are these three, and staging buffer probably will be supported right away as well. And so we just have this here to sort of give the front end an idea of what the buffer is actually used for. But in reality, the back end uses this to actually create the buffer with the appropriate parameters. So next comes a actual render buffer structure, which is pretty much what I discussed before. So we have the render buffer type, the total size of the buffer, the free list memory requirement, the buffer free list rather, the block, and then the internal data, which contains the render API specific buffer. So all of the free list stuff has been moved to the front. The total size and free list items, this holds the type, and then it also contains a pointer to the internal data. So it's pretty straightforward, but we have that separation of concerns there. Okay, so the next thing that we're going to do is go to renderer backend, a structure for this, and we're going to go down to the bottom of it. And we are going to add, once I actually get to the bottom of it, we're going to go ahead and add a interface here to create and manage our render buffers. And so I am actually just going to go ahead and slam in the definitions of these because there's, of course, a lot of comments describing what these are. And they're mostly the same as the interface we've already seen on the Vulkan side. It's just this deals with generic render buffers. So what we're looking at here is we have the create internal, which is used to create the renderer API specific internal buffer for the given information that is provided within the buffer. We have the destroy internal, of course. We have bind, unbind, map memory, unmap memory. We have flush, so that we can basically flush the buffer if we do any kind of write to it. And along those concepts, we have a read. And do we have a write in here somewhere? I don't know if I don't think I actually wound up calling it write. Load range is what we actually have. So we have read, we have resize, we have load range, which just loads a range of data into the buffer. We have a copy range, and we have a draw. The only one that is new out of all of this really is draw. All the rest of these are basically either ported directly from the Vulkan buffer itself or are sort of renames of functions that already exist. So the draw is basically a way for us to issue draw commands on buffers that either an index or a vertex buffer typically in such a way where we don't actually have to be making draw calls from elsewhere in the system. So this is just sort of a shortcut that says, okay, well, based on the type of buffer that it is, we'll issue the proper commands. And we'll see how that's set up once we actually get into it. Okay, so that is what the interface changes look like at the render types level. I'm going to go to the Vulkan types now and make some modifications there because, like I said, we actually have removed some data out of the Vulkan buffer itself. So if I go to Vulkan buffer, we're going to remove some things from here. So first off, the total size we're going to remove because we can actually access that on the front end and we don't need it on the back end. And then we are going to remove the free list memory requirement. So that the free list block, the buffer free list, and whether or not it has a free list. So we don't need any of those properties anymore. So this becomes a much lighter structure and just keeps track of the things that Vulkan needs to know internally and leaves everything else externally. Okay, so the couple of other changes that we're going to need to make are going to be mostly in the other structures. So we have one change to make in the Vulkan shader. Vulkan shader down here. Let's see, where is it? So we have a Vulkan buffer here for the uniform buffer. This is just going to be a render buffer now. And I think that's the only change that we need to make for that. And then also we need to make a change in the Vulkan context. So context, let's see, right here. Let's see, so we have our two Vulkan buffers here, one for object vertex and object index. I probably ought to rename those at some point, but for now it's just going to be Renderbuffer. So I'm just going to change those. And that should be all the changes that we actually need to make at this particular level. Okay, so the next thing that I'm going to do is I'm actually going to start at the back end, make those changes, and then actually no, I'm going to start at the front end, I think. Make the changes there so that we have the interface, because there's actually going to be a couple places where the back end needs to reach out to the front end to call some stuff. So I think it actually makes more sense to do it this way. And so what we're going to wind up doing in terms of the front end is it's going to be almost a direct copy of what the back end is expecting in terms of interface. So if I go here to renderer front end, and I go, I guess probably all the way at the bottom is the best place to put it. I'm just going to paste all this as one big chunk. So if we review this real quick, most of this is comments, of course. But we have the Renderbuffer create. So this is the front end version of all those back end functions that we added. So we have the Renderbuffer create, destroy, bind, unbind, map, unmap, flush, read, resize, allocate, free, load range, copy range, and draw. So most of these are going to be just the basic direct pass through to the back end. So there's not a whole lot yet that's changing. The only things that are really going to be sort of larger changes are going to be the changes that involve the free list. So I'm going to go to renderer frontend.c. And again, most of our changes are actually going to be at the bottom of the file, but the first thing we have to do is go all the way to the top here. And I need to include the containers free list, because we need that here as well, because now the free list is going to live in the front end. And so I'm going to step through this sort of a function at a time. And for the sake of brevity, I'm going to put in the implementation that I've already got sort of off screen here. So the first thing that we're going to do is cover the create. So the create is basically the same as before. All it does is obviously does some initialization, some sanity checking to make sure we actually have a pointer, sets the type, the total size. If we are using a free list, which is a parameter here, we go ahead and create a free list. Otherwise, we don't. And then it goes ahead and calls the internal buffer creation on the back end. So it calls that state pointer back end Renderbuffer create internal that we set up before. And if for some reason that fails, it outputs a fatal error and returns false. If all is well, it goes ahead and returns true. So again, this kind of follows the patterns that we've been following thus far, so there shouldn't really be any surprises here. Likewise, the Renderbuffer destroy is pretty straightforward as well. So we obviously check to make sure we have a buffer first, and then we go ahead and see if that buffer is using a free list. We can just do that by checking the free list memory requirement. If we are using a free list, we go ahead and destroy it, free the memory, and then go ahead and zero that out. Otherwise, either way, I should say, we go ahead and call the backend Renderbuffer destroy internal, which will release those internal backend resources. And that's all there is to that. As far as the bind goes, it's pretty simple. So it just has some sanity checking in here to make sure that we're actually passing something valid here to the buffer. And then it's just a pass through to the backend's Renderbuffer bind. The unbind, in this case, we're just not even going to bother checking anything in terms of whether or not we actually have a buffer here. I suppose we could, but I would think that if you're unbinding something, you would have already bound it and would have found it at that point. So in this case, it's just a pass-through. And in fact, the next several functions are pass-through. So I'm going to paste those all at once. And so we have the map memory, which just passes through to the backend Renderbuffer map memory. Unmap is the same deal. Flush and read are the same deal. Those are just pass-throughs from the front end to the back end. So nothing surprising there. One thing that does have a little bit of logic is the resize. So the resize, first off, does a sanity check to make sure that the new size is at least greater than or equal to the total size. So in fact, we should probably change that to a less than or equal check, right? So it doesn't really make sense for us to be resizing a buffer to the same size that it already is. So we go ahead and say if the new size is less than or equal to the current total size, that's rubbish. We shouldn't be doing that. Error about it and return false. Otherwise, we go ahead and check to see if we are using a free list. Again, that is what we get that rather by checking the memory requirement. If we're using it, then we call free list resize. And if you recall, this actually has to be called twice. One to get the memory requirement and a second time to actually do it. So we go ahead and do that. Then we go ahead and we actually free up the old memory and then copy over the memory requirement, the new memory requirement, and the new block. So that is utilized there. And then we go ahead and call the backend frame buffer resize, which resizes the internal buffer. And then check the result to make sure that it's correct. If it is correct, then we set the total size to the new total size. If it's not, I suppose we should probably also put some error checking in here. K-error failed to resize internal Renderbuffer resources, and we'll return the result here. So that should be fine. Okay, so we'll just go ahead and clean that up a little bit. Okay, so that is the resize. The allocate is pretty much, I think, what you might expect at this point. So obviously it does some sanity checking, and if we have no free list, then we can't actually use allocation, right? Because if we're not using the free list, then that means we're not tracking any allocations, and we're just writing ranges of data directly to the buffer in an untracked way. It means something else is actually tracking that. So if we try to call allocate and we're not using a free list, then we're going to go ahead and warn about that. And we're actually not going to kill the application with that, but we are going to warn about it so that you actually will see that. It does say that the offset will not be valid and that you should call, let's see, Vulkan buffer load data. In fact, that's actually not the correct thing. It should be render buffer load range instead. So it's basically just telling you, hey, you messed up, you called the wrong thing, call this instead. So I am doing that as a warning right now. It may be a good idea to actually do that as an error. I don't know, I haven't decided yet. So for right now, I'm sticking with a warning. So free is very much the same thing. It double checks to see if we actually have a free list in use, and if not, it warns about it and returns true. Otherwise, it calls free list free block on that. And then everything else that we have is actually just a pass-through. So we have load range, copy range, and draw. Those pass through directly to the back-end versions of those things. And so that is all there is to the front end. Again, it's mostly pass-through stuff. The back end really is where most of the work is actually being done. So with that said, the back end, the first thing we're going to do is Vulkan backend.h. We're going to go here to the bottom, and right after our Vulkan renderer is multi-threaded, we're going to paste the definitions, or the declarations rather, of all the functions that we are going to declare. And these are more or less a direct copy of what was in Vulkan Buffer, only with the context removed out of the signature, as well as any of the free list logic, because that's all been moved to the front end at this point. And so rather than sort of doing that individually here, I thought it was a lot faster to just sort of do it all in one shot here. So we have that backend.h change. And as you might have guessed, we actually have a backend change to the C file, which is where most of the stuff actually resides. So let's go to that C file, and we'll collapse this, go to the top. You'll note here that it's bleating about this Vulkan buffer.h. That doesn't exist anymore, so we can get rid of that. And we'll have to actually add a couple of includes here. So the first thing we're going to need to add is a include for the renderer front end. And I'm actually going to put that right here. And the reason for that is because we are actually going to utilize some of the front end functions that we've just declared to actually resize and do some other stuff with the buffers instead of using the internal functions. And there's reasons for that. Typically, it's because we need to leverage the free list logic if it's actually being used. So we do need that. And then let's see. So the next thing we'll need to do is come down here, and we have this create buffers function, which is actually, whoops, didn't mean to full screen that. We have this create buffers, which is actually going through here and creating our Vulkan buffers by calling our Vulkan buffer create and all that, which these things don't actually exist anymore. And so we're actually going to remove this create buffers. So I'm going to kill it here, and then go back here at the top and remove create buffers there as well, because we no longer are going to be creating buffers in that way. We're actually going to kind of do it inline during the initialization. The next thing that we're going to need to do is we are actually going to have a new private function here. Right under create module, we're going to have Vulkan buffer copy range internal. And this is just a shortcut method that we're going to use as a convenience anytime we need to copy between buffers. Basically, well, I'll actually walk through that when we get to it. So this is all the custom allocator stuff, so I'm just going to collapse this so I can get past it. So this upload data range bit here, this is actually going to be going away as well. And so let's see, we can just nuke this. We don't have a forward declaration of that, so we can get rid of that. Also, this free data range, we don't need that anymore because we could just call the front end version of that. So more code that we can remove. Always a good thing. So the next thing that we're going to need is where we are calling create buffers. I think that's the only place left. Yeah. So where we're calling this is where we're actually going to switch to doing this inline. So we're going to remove that, and we are basically going to create and bind our buffers. So I'm actually going to just slam this whole block of code in here and then explain it. So we create our geometry vertex buffer by using our front end Renderbuffer create. And this is going to, of course, mimic the logic that was there before, so we're keeping the same sizes and everything. But you can see here we're passing the type of vertex for this one, the size, this use free list here is true. And then, of course, the address of the vertex, the object vertex buffer object. And so if that creation fails for any reason, we bleat about it, and then we return false. Then we go ahead and we bind that buffer. And we bind it just from the offset of 0, so the very beginning of that buffer, because we're going to wind up basically using the whole thing, at least for now. And so we do that for the geometry vertex buffer and the geometry index buffer. And so we just do the same thing here. We just pass the different information for the index buffer. So we have the type here, the size, and of course the address to hold that buffer. And again, if it fails, we bleat about it and return false, and then we go ahead and bind that as well. So with that, we also have to come down here to the render backend shutdown, and we are going to basically replace the two methods, or the two method calls really, to these destroys. And instead of calling Vulkan buffer destroy with a context, we are going to call Renderbuffer destroy and pass the address of the context object, vertex, and index buffers, as you might expect. Okay. So the next thing that we'll need to do is we actually need to fix a small bug. So I'm going to go to Vulkan renderer texture create. And I'm going to resolve a tiny bug that we have here in the size. So currently right now, this size is actually looking at the width times height times channel count, which is correct unless we are using a cube map. That would be my phone. Should have put that on D&D. All right, anyway. So what we need to do is we need to take a look at the texture type and multiply that by either 6 if it's a cube map, or 1, which basically does nothing if it is not a cube map. So that was a tiny bug, but one that needed to be fixed nonetheless. Okay. So now that we've done that, we actually need to go into Vulkan renderer texture write data, which I think is not too much further down, right here. And we need to make some changes here as well. So the first thing that we need to do is get rid of this image size, because we're actually not going to wind up using it. So we can get rid of that line in its entirety. And the image format can stay, but all of this stuff about creating the staging buffer and loading data into it, this can all actually go away. So I'm going to remove all of this because we're actually going to use our new methods for doing that. So the first thing we're going to do is stand up a staging buffer. And so the render buffer create, we're going to call the staging. It does not use a free list, right? We're just going to jam the data in there all at once. So we do not need a free list for that. And then, of course, if that fails to create for some reason, we're going to bleat about it and boot out. Otherwise, we will bind the buffer. All right. And then essentially what we're going to have to do, excuse me, is come down here to our Vulkan image copy from buffer. And we're going to just have to make a quick change to actually get this handle, because the handle is not really in the render buffer. It's in the internal data of the render buffer. So we're actually going to have to cast this staging. So we'll cast that to a Vulkan buffer pointer, right? And then we'll say staging.internal data, and then handle. And that will actually give us the handle that we're looking for, the VK buffer. Okay. So we've got that there. And then down here at the bottom, we need to make one more change. So we have this Vulkan buffer destroy for the staging buffer. We actually need to first unbind that and then destroy it. So we're going to call, again, the front end methods for doing that, which basically just pass through to the back end methods, but it's for convenience sake, it's a little bit better to do it this way, as well as if we ever change the destroy to include anything else, we want to make sure that we're cleaning up all those resources as we should be. So that is it for that. The next thing that we're going to need to do is in our create geometry, because it is also using buffers, and so that's going to change somewhat. And so the very first section of this is actually down about halfway through the method or so, maybe a little bit less than halfway. Where we are getting the pool and the queue, we no longer need that. And in fact, if we come down here, we're going to keep the vertex count, element size, and total size. We need those. But this call here to upload data range, we're not going to be doing that anymore. Instead, we are actually going to be replacing this with two different calls. So that is going to be replaced with first allocating space in the buffer. So we are going to call Renderbuffer allocate on the vertex buffer first, the total size, and we're basically just going to allocate some space in there, right? And this is the total size of the geometry that's being uploaded, not the total size of the buffer. So we're going to allocate that space in the buffer, and then we are going to load the data within that, okay? And just format that, all right? And so since we've done that to the vertex buffer, we also need to make those same changes to the index buffer. So I'm basically going to come in here and do the exact same thing. So I'm just going to grab all of this right here, actually. So we want to leave these 3 lines here for the index count, element size, and the total size, because we still want to use those. And we're going to call, again, Renderbuffer allocate, passing the object index buffer, the total size that is computed for the indices, and then the offset there to get that offset. And then we'll go ahead and call load range on that and load in the indices as you might expect. Okay. So there are a couple more things that we need to address in this function. So we have this free data range, which no longer exists. So as you might have guessed, we are now going to use the front end version of that. So we're just going to replace that with the Renderbuffer free, of course, passing through the relevant properties. So that is that. And obviously, if we have index data, we are going to replace this free data range with the Renderbuffer free, of course, passing through the relevant properties of that. Okay, so I think that's it for that function. We're also going to need to take a look at destroy geometry because it also calls free data range in these two places. So these calls are going to look pretty much exactly like the other ones. So I'm just going to replace this free data range with Renderbuffer free. And then if we have index data, I'm going to do the same thing here as well. And that will take care of that. And then the next thing that we're going to need to do is come down to our draw geometry, and this is where the Renderbuffer, or the Renderbuffer draw is going to get come into play. So what we're going to do here is we are actually going to just use the backend calls directly in this case, just because it's a little bit quicker and easier, because the draw is literally just a pass through, so there's no sense in this case of doing it any other way. And so basically what we're going to wind up doing is we are going to clear out, let's see, we need the geometry data. We do not need the command buffer, so we can get rid of that. We do not need any of this. And then in here, we do not need, in fact, we do not need any of this. I think all we actually have to do, in fact, actually, let's just get rid of this whole thing. Let's start from scratch. I think that'll be a lot cleaner. So the first thing that we're going to do is we're going to run a check to see if we actually have index data. That's going to look at the buffer data index count. And then we'll go ahead and call Vulkan buffer draw. So that is going to take the vertex buffer, the vertex buffer offset, the vertex count, and whether or not it includes the index data. So that is going to be passed to bind only. And basically what that says is if we actually have index data, we're not going to do a draw call against this buffer. We are only going to bind it. And if it does not have index data, then we would go ahead and bind it and call draw against it. And that's for the type of vertex buffer. And you guys will see that once we actually get into that backend logic there. So the second part of this is going to be right after this, which is basically going to say if we have indexed data, we're going to call draw against the index buffer, passing the offset, the count, obviously, and then we're going to pass the opposite of includes index data, which in this case is going to flip that around. So if we do have index data, I suppose we could just literally pass false here. And it would pretty much wind up being the same thing. In fact, I think that's a little bit clearer. So in this case, we are going to bind that buffer and call draw against the index buffer if we have index data. So that is that. And I think that's it for that function. So the next thing we'll need to do is we'll need to go to actually our shader destroy. Because I don't think our create actually needs any updates, but our destroy definitely does. So when we go ahead and destroy the uniform buffer, we are calling functions here that no longer exist. And so we actually need to replace these with the Vulkan buffer unmap memory. So instead of unlock, we've actually renamed that to unmap, just to sort of be consistent with what's going on in the back end. So that does not take the context anymore, but does take an offset, which in this case is 0, and we're passing VK whole size to indicate that we are basically going to unmap the entire buffer. And then after that, we go ahead and zero out that memory. Instead of calling Vulkan buffer destroy, which no longer exists, we call Renderbuffer destroy. And this literally just takes the uniform buffer and no longer requires the context. All right, so the next thing is shader initialize. So we've got a couple changes in here that we need to make. The first thing that we can do is we actually need to come down here. Let's see. So that's the pipeline. Here. So for the uniform buffer, this stuff is going to be wrong now because of the way that we handle buffers. So there's actually logic within the buffer itself to detect whether or not it's device local. So we actually don't need this check here at all anymore. So I'm going to remove that. The total buffer size can stay exactly like it is. The only thing that we're going to wind up changing, at least for this particular block of code, is we're going to take this if check for the Renderbuffer or the Vulkan buffer create. Since that doesn't exist anymore, we don't have to pass all this crap. All we need to do is call Renderbuffer create, passing the type of uniform for that. Total buffer size, we are going to be using a free list, and then of course a pointer to hold that buffer. And like we have done otherwise, after we create it, we're going to go ahead and bind it. So we want to go ahead and do that. And then we have our call here to allocate. And instead of calling Vulkan buffer allocate, which again doesn't exist, it's been replaced by Renderbuffer allocate. And let's see, yeah. Right. Okay. So we've got Renderbuffer allocate there, and that is, I think, the only thing we actually need to do. I think the signature for that is actually the exact same thing. So Next, we have the change of the lock memory to Vulkan buffer map memory. And again, that's just a sort of pass through, so we're just going to use that sort of as it is. So I'm going to change this from Vulkan buffer lock memory to Vulkan buffer map memory. And then we actually don't need all of this stuff anymore. So we don't need the context anymore. We are just going to pass the buffer, offset, and size. And this last property is no longer needed as well, this 0, and I'm going to get rid of that comment as well. All right, so that is that. And then we just have to perform a couple of casts, which are actually down here in the shader. I think it was apply instance. Apply globals. Apply globals and apply instance, I think both have it. So instead of saying the buffer is internal uniform buffer handle, this is actually going to be uniform buffer internal data, which is a void pointer, so we need to cast that. So that's going to be Vulkan buffer pointer, and then surround that with that. Okay, so we get the handle properly there. And then we're going to come down to apply instance, and we're going to basically have to do the same thing wherever that exists. So we'll go here and we'll just cast this to a Vulkan buffer pointer. I'm just going to copy this because I'm going to have to do it one more time. And this is going to be internal data and arrow to handle. Okay, so we've got that, and I thought there was one more place in here that we had to do. I could be wrong. Oh, I guess that is it. All right. Okay, so let me just make sure. If I missed one, I'll catch it when I recompile. Let's see. So one thing that we should probably be doing is when we are releasing texture map resources, we should probably, before we destroy this sampler, we should probably make sure that there's no way that it's in use. I'm going to kind of go with the nuclear option here of calling VK device wait idle. And that just ensures that this is not going to be in use when we actually go to destroy or release these resources. Because every once in a while, this can actually cause a validation error when you shut down if you don't do it. Again, there's probably a better way that we can handle this. We could probably just stop the render loop, let everything finish out, and then handle it that way for the shutdown purpose. But while we're running, that can actually get a little bit tricky as well when we go to unload things. So for now, I'm just going to plop that in there. All right. So if we go to a little bit further down, there's one more change that we need to make for acquiring instance resources. So within this method here, we had a call to Vulkan buffer allocate, which of course no longer exists. That has been replaced by Renderbuffer allocate. So it takes the same properties, so that should be good to go as is. And then a little bit further down in releasing the resources, we are calling Vulkan buffer free, which no longer exists. So we're going to replace that with Renderbuffer free, passing through basically the same properties. We'll bleat about it if it fails for some reason, but there's not really much we can do about it. So I'm not going to bother kicking out of the method or anything. Okay, so with that said, now we are at the point where we can actually start putting the backend Vulkan buffer stuff back into place. So the first thing that we're going to do is we're going to notate that this is sort of the start of a region for the Vulkan buffer stuff, just to kind of separate it out a little bit visually. And we've got a couple of sort of internal checks that we're going to use, which is Vulkan buffer is device local, so it just basically takes in a buffer, looks at its memory property flags, and then does that local bit change check rather. We have another check for host visible that does host visible, host coherent for host coherent. So those are just convenience so that we don't have to do all this inline everywhere. So the next thing that we're going to do is we're going to go ahead and set up our create internal. And this one I'm actually going to sort of chunk out a little bit so that we can explain it. Because this is where a lot of the switching happens based on the type of buffer that you set and pass in. So obviously first we want to do a sanity check to make sure that we have a pointer to a buffer. And then we go ahead and stand up an internal buffer. And we're going to switch on the buffer type. And in this case, I'm actually just going to slam in a bunch of these switch definitions because it would take way too long to type all this out. So if we have a vertex buffer, we're going to set the usage to vertex buffer bit. We're also going to set it as a transfer destination and a transfer source. We might tweak this a little bit later to make it a little bit more configurable so that if we don't need these flags on, we don't turn them on. But for now, we're just going to leave it as is. And then, of course, the memory property flags is we are going to use device local memory. At least for right now, that's the way we want to do it. We probably need to run some checks to see if we can actually do that because we may not actually have that on all cards. I'm not 100% sure. But for now, that's what we're going to roll with. And if anybody has an issue where that doesn't work, they probably would have discovered it before this. But if anybody has an issue with that, just let me know and we can fix it. So next, we do the same type of thing for the index type. We just use the index buffer bit instead. For uniform buffer, we go ahead and do a check to see if the device supports local host visible. And if so, then we go ahead and we set some bits here, specifically the device local bit. Now in this case, we're just setting it to 1 or 0, whether or not it depending on whether or not it supports that. And then what we'll do here is the usage, of course, is transfer destination and in the uniform buffer bit. In fact, just because the lack of consistency is going to bother me, I'm going to switch the usage to the front and then the transfer destination to after that. And then we have the memory property flags, which is host visible, host coherent, and it'll OR the device local bits, so that'll either OR 1 or 0, depending on whether or not it's supported. Okay, so next we have staging, which staging, its only usage is a transfer source. So that's the only thing that is actually used for. And then we have host visible and host coherent. That's all we need for that. For a read buffer, we have this as a transfer destination bit. And then we go ahead and remember this is reading to that buffer, right? It's a read buffer from memory. So we go ahead and set up the property flags of host visible and host coherent for that as well. In the case of storage buffers, we don't actually support those yet. I will be adding those at some point because we are going to want to use that. But for right now, I don't have the backend to support it. So I'm just going to bleat about it and return false. If we have a default case, meaning we pass some sort of type that doesn't exist in here, or it's the undefined type or something like that, we bleat about it saying, this type is unsupported and return false. Nothing too crazy there. All right, so the rest of this is actually all stuff that we have seen before. So the only difference is we actually just have a lot of this switched ahead of time. So I'm going to go ahead and paste this in. And we have our buffer create info. Again, this is pretty much the exact same stuff we had before. It's just formatted slightly different and a little bit more dynamic. We go ahead and create the buffer, gather the memory requirements, allocate the memory, determine whether or not it's device memory, and then we call our kallocate report if the memory is device memory, we say, hey, this is GPU local memory. Otherwise, we tag it as Vulkan memory. And then we check the success of that. If for any reason it's unsuccessful, we bleat about it and return false. Next, we allocate the internal state of block memory at the end once we're sure that everything has created successfully. So this is where we go ahead and we say, okay, let's go ahead and allocate some space for our Vulkan buffer, our internal buffer. And then we essentially just copy the internal buffer, everything that we've set up here to this guy. We just copy that into that pointer, and then we have our internal resources created. Okay, and then of course we return true. So that is the creation. The destruction basically just undoes all that, and there's not really anything too special here, so I'm just going to slam this all in here at once. It frees memory, destroys the internal buffer, reports the freed up memory, zeroes stuff out, frees, of course, the allocation of the internal buffer and zeroes that out, and that's all there really is to it. The resize is also pretty much the same as it was before. So again, I'm not really going to step through this in too much detail. Sanity checks, grabs the internal buffer, and then it goes ahead and creates a new buffer. We have memory requirements for that new buffer. We go ahead and allocate that memory here. We go ahead and bind it. We copy over the data from the old buffer to the new buffer. Make sure that nothing is using it, the current buffer, before we destroy it. Then we destroy the old buffer, freeing its memory as well. We go ahead and report the free of the old and the allocation of the new. So again, we do the device memory check. We report the old free and report the new allocate. And then we go ahead and we set the new properties. So we set the memory and the handle to the new memory and new buffer and return true. So nothing too trailblazing there. Next is binding. So again, sanity checks, grab the pointer to the internal buffer, and we call VK bind buffer memory. Nothing too special about that. Same for unbind, except right now, unbinding does nothing. In OpenGL, there actually is a way to sort of unbind things by passing 0. Vulkan, as far as I'm aware, doesn't really have any equivalent of that. But nevertheless, that interface still exists. So we are going to check to make sure that we're not at least passing this or calling this against a null pointer. So next we have map and unmap. And those two things are pretty much exactly the way they were before. They just have a sanity check and a cold cast to get the internal buffer, and then map and unmap as you would expect. Flush is pretty straightforward as well. So again, sanity check, cold cast internal buffer, does a check to see if the buffer is host coherent. If it is not, then it goes ahead and grabs a mapped memory range and then flushes the mapped memory ranges. So you only have to do this on memory that is not host coherent. So if it is host coherent, it kind of automatically happens. So this is just a manual way to be able to handle that if it needs to be handled in the first place. Okay, so next we have a Vulkan buffer read. So this isn't anything too special either. It basically determines whether it's device local, whether it's host visible or not. It goes ahead and creates a read buffer here. So there's an example of where that's used. And then it'll basically read from whatever you actually pass into it. So if we have this buffer here, we can actually read into another buffer and write out to this memory here. That's essentially all we're doing. So we're essentially creating a temporary buffer to read from a specific range of this buffer and output it as a basically contiguous block of memory here. So depending on whether the device is local, using local memory or not, and is host visible or not, depends on what we need to do. So if it is device local and not host visible, then we actually need a read buffer. If we don't need a staging buffer, then we can just map it, copy, and unmap it. So depending on how the incoming buffer is set up, determines what we basically have to do there. All right, load range is, I don't think, changed pretty much at all, other than just, grabbing, cold casting to this internal buffer, or sanity checks and stuff like that. This is pretty much the same story as the read up here, only instead of reading, we're writing. So it's pretty much the same layout. It's just we create a staging buffer, we bind that staging buffer, we load the range into the staging buffer, so the data range from here. We load that whole thing in there, then we copy from the staging buffer to the buffer that we've passed in, and then we go ahead and unbind and destroy the staging buffer. If there's no staging buffer that's needed, then we map, copy, and unmap. So pretty straightforward stuff. All right, so the next thing that we need to do is we need to define copy range internal. And so this, I have a to-do in here, which we're making the assumption that we're using the graphics queue for this, which is probably not right. We probably eventually should have this be configurable. I'm just not 100% sure how I want to set that up just yet. So I'm making this assumption for now because it's really the only queue that kind of matters for this type of stuff anyways. So we're just going to use the graphics queue for that. We might eventually have like a copy queue that we use, but for right now I'm not going to bother. So we grab that, we make sure that it's idle before we do anything. We go ahead and set up a single use command buffer, and then we call VK command copy buffer, and we have our source, destination, our copy region, all that. And then we end the single use buffer and return true, and we're done. So again, not too much groundbreaking there. It's pretty much all stuff that we've seen before. So here we have Vulkan buffer copy range. And so this basically just calls copy range internal. It does a little bit of sanity checking here, but it just kind of makes this a little bit easier to use and exposes it to the front end. So the front end can call this. This basically formats and casts what is needed, and then it calls this here. And finally, the last function here that we have is draw. And this is where that logic is that I was telling you that varies based on the type of buffer. So if our buffer type is vertex, then we go ahead and say VK command bind vertex buffers. So we go ahead and call that using the buffer offset element count that we passed in. If bind only is false, then we go ahead and also call VK command draw against that, passing the element count, of course, and then we return true. So in our case, we, at least for our geometry buffers, we are going to have an index buffer. So in our case, that would be bind only would be true in that case, and so this wouldn't get called. And then we have our else if here for our index buffer type, and so of course we bind the index buffer, and then if it's not bind only, again we call command draw indexed. So in our case, when we actually draw our index buffer, we are passing false for bind only because we actually do want to draw that. And so this will wind up getting called. So this basically replaces that logic that we had sort of in our main render loop up above. And then of course, if the type is anything other than vertex or index, we go ahead and bleat about it saying we cannot draw a buffer of type, spit out the type, and then return false. And that really is it as far as the back end goes. So it looks like a lot of code. I mean, it is a lot of code, but a lot of it was honestly just copied over directly from what we had already written in the past. And so it's not quite as much as it looks like. We're just, we moved around a lot of stuff, but we didn't really add too much that's new. Okay, so the next and final thing that we need to do in this video is we need to go to renderbackend.c, and we need to actually hook these up because we haven't actually hooked this up to our interface yet. And so I'm going to go ahead and just slam these all in at once because there's no point in you guys watching me type all that out. So this is just hooking up all the function pointers to the front end. All right, I'm going to clean and rebuild. And what did I miss? Anything? It built successfully anyway. What is this bleating about? Why is it? Okay, that must be VS Code having a connection or something. All right, so I didn't get any compilation errors, so let's go ahead and run. And that ain't right. That's definitely not right. What happens if we load everything? Yeah, that's definitely foobar. So we missed something. All right. What did we miss? Just gonna run it one more time for sanity's sake. That kind of looks like the cube. That is the cube. You can kind of see them there. Trying to think what all we could have. I wonder if it is. I wonder if it's this. I don't think so. That should always be false. But let me put what was there originally. Maybe that messed something up that I'm not thinking of. Nope. Okay. So let's have a look at what we have changed. Because I'm thinking I probably just fat-fingered something. So this is just create, destroy. These guys are all just pass-throughs. Really can't picture it being any one of those things. So we have our create. I don't see anything here that looks. Let me go to the. So this all looks pretty good. Destroy wouldn't have anything to do with it. Bind, these are all just pass-throughs. Resize we're not really doing. Allocate, let's see. This is really... Oh, wait a minute. Renderbuffer. So we're doing... Yeah, these are all pass-throughs. We only need to handle the free list logic here. So that makes me wonder if it is something on the back end that I got wrong. So we've changed that. Let me see what these changes are here. Copy. Renderbuffer create. So that's the vertex. Nope, I don't think I got anything wrong here. This all looks good. So I don't think it's that. It's not going to be anything having to do with the destroy. The texture create, I don't think it's going to be the texture either. This seems like a geometry problem. At least that's kind of how it looks. I might have to crank up render doc here and have a look, but so the only thing that I changed here was having to do with this. Let's see, so write data was another place I changed some stuff. That's staging buffer. That's using size correctly. Yeah, this Oh, wait a minute. Let's see. So we have so we created our staging buffer. And we're copying from the staging buffer. Did we not actually rebound? I don't think we didn't actually load anything into the buffer range. That would cause a problem. So Vulkan buffer load range. We'll pass the address of staging. The offset is going to be 0. We want the size of the image. And then the data is going to be the pixels. Surprised that didn't completely... I guess it's just using whatever garbage data is already in there. Okay, let's try that. There we go. Okay. So that was a dumb mistake, but happens. All right, so let's go ahead and load this up. And it looks like we are good to go. So we have our generic render buffers in place, which, you know, represented quite a lot of work, but we're going to need that generic aspect of it in order to actually implement our next feature, which I don't want to give away just yet what that is, but it's going to be a pretty useful and big feature that you need for any engine, and it's going to allow us to improve things like debuggability and eventually tool sets and things like that. So with that said, I'm going to go ahead and cut the video here. Thank you guys so much for watching. I hope you're enjoying the series. I hope you're learning. If you haven't already, toss me a like and subscribe if you haven't already subscribed. And hit the little bell icon there so you get notifications as to when new videos in this or my other series drops. And I will see you guys next time.